Okay, folks, I want to go ahead and do a quick video where we derive the Laplace transform for the expression. Let's do the Laplace transform for the expression, the cosine of AT, and we'll also derive the Laplace transform for the sine of AT. And we're going to derive both of them simultaneously, and it's kind of a trick, I guess. And we're going to use it based upon already knowing the Laplace transform of e to the at. So we look at the Laplace transform of, we know that e to the at has a Laplace transform. We derived this in class. We know that its Laplace transform is 1 over s minus a. Of course, this only holds. We only get convergence if s is greater than a. So let's go ahead and use this fact as well as Eulers formula, and we'll go ahead and find the Laplace transform of these two functions, which is a huge time saver because each one of them involves integration by parts twice and evaluation of some little more difficult limits we care for. So we know that the Laplace transform of e to the at is this expression. So if we go ahead and take the Laplace transform of e to the AIT, well, just following our work from before, this gives us 1 over s minus AI. And what I'd like to do is I'd like to go ahead and rationalize this complex number, or get rid of the complex number in the denominator. So the trick for doing that, always for changing a complex expression into a real expression, is to multiply by the complex conjugate of that number. So we're going to multiply this by s plus ai all over s plus ai. And when we do so, it's a little fast, when we do so, we get s plus ai all over s squared plus a squared. Remember, when you multiply a complex number by its conjugate, you simply get the real component squared plus the imaginary component squared. So that's how we do that multiplication. So we can now go ahead and split this up into two fractions. We can write this as s over s squared plus a squared plus ai, and I'm going to go ahead and put the I out in front, a s squared plus a squared. Okay, so how does that help us? Well, a while back we derived Euler's formula using power series, and we know that e to the AIT could be thought of, let's first think of it as, and we'll just do this to review Euler's identity. We don't actually have to rewrite it this way, but let's go ahead and write it this way. We could write this as 0 plus AIT. So now I've got the real part and the imaginary part. And Euler's formula says we can go ahead and rewrite this as e to the 0t, which is just 1, that's why we didn't need to write it, times the cosine of AT, put that in parentheses, plus I, the sine of AT. Well, I guess let's take a line and drop that e term, since e to the 0t is just 1. And so we get the cosine of AT plus I sine of AT is equivalent to computing what we just did. Well, there's one more step we need, and that requires us to utilize the linearity of the Laplace transform. Remember, the Laplace transform is a linear transform, and so what does that mean again? It means that the transform distributes over the addition of the objects, in this case our objects are functions, and scalar multiples, in this case real numbers, or, well, actually I should say complex numbers, factor out of it. So we could go ahead and rewrite this as the Laplace transform of the cosine of AT plus I times the Laplace transform, it's a rough L, the Laplace transform of the sine of AT. And now we can just make a comparison of components. We've got that the Laplace transform of the cosine of AT plus I times the Laplace transform of the sine of AT needs to equal s over s squared plus a squared plus I a over s squared plus a squared. And now we make the classic position argument that we've been making all semester. Keep in mind that what does the Laplace transform do? It takes a function in t space and maps it to s space. So this is an expression involving s, and this is an expression involving I times s. And so by equating like terms, we get the big result, the result that we were after, that the Laplace transform of the cosine of AT is just equal to s over s squared plus a squared, and the Laplace transform. Let's try it. Third time's the charm here. The Laplace transform of the sine of AT is equal to a over sine squared plus a squared, where I equated this Laplace transform to the imaginary part of our answer that we derived. So that gives us the Laplace transform of the cosine and the Laplace transform of the sine. And so the last thing I want to do, so that's the bulk of the work. The last thing I want to do is be a little bit more careful in talking about where does this Laplace transform hold. And we're going to show in just a minute that this Laplace transform holds for s greater than 0, and this holds also for s greater than 0. The only thing I want to do is go backtrack a little bit right here. So we had this fact here that the Laplace transform of AT would hold as long as s is greater than a. When we applied the Laplace transform here, we're dealing with a complex number, and when we originally derived it, we thought of a as being usually we think of a as being a real number. What we really mean, and we could go back and be a little more careful here, what we really mean is we need s to be greater than the real part. We need s to be greater than the real part of some complex number, alpha plus beta I. So that's what we actually need to get the convergence of the Laplace transform here. Normally, if a is a real number, then we just say s needs to be greater than a. But if s is a complex number, we need s to be greater than a alpha plus beta I. So in this case, what is the real part for this Laplace transform? Well, the real part here, if the number is 0 plus ai, the real part of that is 0, and so we just need s to be greater than 0, and so that holds when we make the equality amongst the components, and that's why it's good enough to say that s needs to be positive. We don't need to say that s is greater than a when we deal with the Laplace transform of the cosines and the sines. Folks, I hope that was helpful. Let me know if you have any questions.